Okay, love this one. What is a counterexample? If you have some conjecture, for example, in this case, the conjecture is any number that's divisible by 4 is also divisible by 8. They're making some claim that this is always going to be true. And you say, aha, well, it's not always true. And they say, well, if it's not, how can you prove to me that it's not always true? The way that you prove something is not true is to provide a counterexample. If you could just show one example where it's false, then you say, well, if I can find even one example where it's false, then it's not true in all cases. Because if it was true in all cases, we'd never be able to find a situation where it wasn't true. So, finding a counterexample is finding at least one situation where it's not true, meaning it's not true all the time. Okay, so what's a counterexample for this? Any number that's divisible by 4 is also divisible by 8. So we would need to find a number that's divisible by 4, but then it doesn't fit this part. That's not divisible by 8. This is divisible by 4. This is divisible by 4. This is divisible by 4. This isn't. That's not a multiple of 4, so it doesn't fit the first condition. So it's irrelevant. It's not going to matter to us. This number is not going to be a counterexample because you have to. This is saying if you can fit this condition, you guaranteed will also fit this condition. So the first thing we need to do is fit this condition and then find a number that does fit that, but not that. Well, this one doesn't even fit the first condition, so we're going to cross that out. Okay? Now, we need to not fit divisible by 8. So 24, is that divisible by 8? Yeah, that's actually 8 times 3. So that's divisible by 4, also divisible by 8, does not disprove the conjecture. That's no good. Interestingly, same thing with B. This is a multiple of 4, sure, but it's also a multiple of 8. So that doesn't disprove the conjecture. So far, A and B are demonstrating that a number that's divisible by 4 is also divisible by 8. So that's not a counterexample. Aha, oh, we got rid of D. C, that's divisible by 4. 12 divided by 4 is 3. Perfect whole number. But it's not divisible by 8. If you do 12 divided by 8, you actually get 1 and 1/2. That's not divisible if you're not getting a whole number. So that's a counterexample. Great. Now, using counterexamples to disprove things. Number 44, is the statement a good definition? If it's not, find a counterexample. Anytime something's a good definition, if it is a good definition, you won't be able to find a counterexample to it. So, a square is a figure with 2 pairs of parallel sides and 4 right angles. Well, look at this. Look at this. This has, this has 4 parallel sides. 2 pairs of parallel sides, 4 right angles. Here's the parallel sides. That is parallel to that. And here's another set of parallel sides. That's parallel to that. And we could say that shows that they're parallel. Okay. And 4 right angles. How do we do right angles? Well, this is a rectangle, so we know that those right angles are there. Right angle, right angle, right angle, right angle. 4 right angles, 2 pairs of parallel sides. That fits the definition, but is it a square? No, it's not. It's not a square. So we can find something that actually fits that definition, but is not a square. So that is not a good definition, and we found a counterexample with, what is that thing in yellow that we're seeing there? It's a rectangle. So no, it's not a good definition. A rectangle is a counterexample, as you can see. Okay. And this is kind of working backwards because you should already know this after us just talking about this. But one way to show that a statement is not a good definition is to find a counterexample. If you can find a counterexample, one situation where the statement is not true, then It's not a good definition, and we have to scrap it as a definition because it's got to either be true in all cases or not a good definition. There you go. Counterexample. Good, important tool in your toolbox because, wow, somebody can make some broad claim and you can just say, boom, all I need to come up with is one thing that makes it not true. This is good in any kind of debating situation where you're trying to explain or convince somebody of something or talk about something and they're making a statement, blanket statement of, this is always true. What about that? What about this situation? And all you have to do is name one and then prove that it's a faulty definition. So it's good outside of mathematics too. Okay, we're done.